trace properties. Quite often we formulate a problem to be solved by an input-output automata or an algorithm as a property on the sequence of events at the external interface of the automaton. We call these properties trace properties. Properties of input-output automata are formulated as properties of their fair traces. So an input-output automaton can be viewed as a black box from the point of view of a user. What the user sees is just the traces of the automaton's execution. A trace property specifies both the external interface and the set, or other word property, of sequences observed at the interface. So a trace property specifies the signature of P contain no internal actions, only external actions, and the traces of B is a set of sequences of actions in the signature P. The idea of an automaton A satisfying a property P is basically to satisfy the following property: that every external behavior of A that can be produced is permitted by the property P. Now we can specify this to mean either one of the following. So A satisfies a trace property P can mean either, first, the external signature of A is the same as the signature of P. That's normal. You have the same kind of events. And the traces of A is a subset of the traces of B. So here is the traces of P and the traces of A, and the traces of A here is a subset of the traces of B. The other alternative is that, of course, they have the same actions, external actions, but the fair traces of A is a subset of the traces of B. In fact, for most of the problems, this is what we are interested in, that the fair traces of A are a subset of the traces of B. Let us now look to an example to see what it means for an automata to satisfy a problem specification. So the automaton A and the trace P has the same signature. This is a set of input actions, and this is a set of output actions. Now, the problem P has the following traces. The problem P has the traces, which is a set of all sequences of 0, 1, and 2 that include at least 1, 1. Now we want to design an automata that satisfies this problem. And it's very trivial. We just have an automata A that has a single task, and this task executes output actions, and the output action just outputs 1. Now, if we look to the fair traces of A, so any fair trace of A will have the output action performed, or the task executing the output action will be performed. Therefore, in any execution, we will get at least one output with the value 1. And therefore, the fair traces as a set is a subset of the traces of P. On the other hand, the set of traces of A is not a subset of the traces of P. It is possible that in unfair execution, we refrain from executing the action that produces the output 1. That's one thing. And also, a possible unfair trace is a trace that does nothing. And of course, the traces that only executes the input actions, which is basically 0, 0, 0, and so on. We are going to talk in lecture 3 in detail about safety and liveness properties, but here we'll do some concise description of that. If this seems a little bit cryptic, just wait for lecture 3 where we do a detailed study of safety and liveness properties. A safety property states that some particular bad thing never happens in any trace. That's what a safety property says. And when we talk about bad thing, it's often a bad event in the trace that causes a violation of safety. Let us now define what is a safety property. So a trace property P is a safety property if the following conditions hold. There are 3 conditions. The first condition says that the traces, the set of sequences, cannot be an empty set. That is saying that you cannot satisfy safety by refraining to do anything. The second property says if we have a sequence beta, which is element of the traces of B, it means that beta satisfies the safety property. Then every finite prefix of beta is also in the trace of B. This is saying that if nothing bad happens in beta, and then nothing bad happens in a prefix of beta. The next property talks about infinite executions or infinite traces. So we're looking to executions that are infinite, and we're looking to the traces of these executions. And it says that if beta 1 and beta 2 and so on is an infinite sequence of finite traces in the traces of P, in these, so they are good traces, they satisfy the safety properties, whereas beta I is a prefix of beta I plus 1. Means, for example, beta 1 is a prefix of beta 2, and beta 2 would be a prefix of beta 3. Then at the limit, beta is also in the traces of B. So it means that beta will satisfy the safety property, which is saying that if something bad happens in this infinite sequence beta, then a bad event must have happened in a finite prefix of that. And this now is avoided by making sure that all finite prefixes are good prefixes. You don't have a bad event. So here is an example of a trace property P that is a safety property. So we know this from this lecture. We have the set of or init V from a fixed set V. This is the input event or action. And we have the side V as the output set. So the following is a safety property. If we look to define the traces of P. It is a set of all sequences of init and decide, where no decide occurs without a preceding init for the same value V. So if we see a decide without a preceding init, it means a bad event happened. We are going to take much more examples when we are doing the study of distributed algorithm later, and we will classify many of the properties of problems and distributed abstraction as safety and liveness properties. So now let us look to liveness properties. So informally, a liveness property says that some particular good event or good thing will eventually happen. A good thing could be the termination of an algorithm or the occurrence of a specific event. A trace property P then is a liveness property. So a trace property is a set of sequences, as you know. If every finite sequence that have P's signature has some extension that is in the traces of P. What we are saying here, if we take any finite sequence no matter at what has happened up to this point, it is possible to take this finite sequence and extend it. That means it is possible for the good occurrence of an event to happen at some time later in the future. Here is an example of a trace property that is a Leibniz property. We have the same signature as before, the init V and the side V, and our Leibniz property says P, or the traces of P, is a set of all sequences init V and the side V, where for every init event in the sequence there is a corresponding decide event later in that sequence. So the good thing is that the decide happens. We will now relate safety and liveness properties as trace properties with two important results that we will not prove. The first theorem says if P is a property that both satisfies the safety property and satisfies the liveness property, then P is a set of all sequences of actions in the signature of the problem P. So this says that there are no non-trivial trace properties that are both safety and liveness properties. The second theorem says that if P is an arbitrary trace property and this trace property set is not empty, then there exists a safety property S, that's another set, and a liveness property L, that's another set, so that the intersection between these two sets is the property, the arbitrary property at hand. So this says that any arbitrary property is a conjunction of a safety property and a liveness property. This is the intersection. These are the sequences that satisfy both the safety and liveness. By this, we end this unit on trace properties.